All right, we are recording. Okay, so section 4.3 entitled phase shift. All right, ladies and gentlemen, here is the graph of y equals sine of x plus pi halves. Now, x plus pi halves is the argument or the input that goes into this sine function here. All right. And they want to restrict the domain of this function for input values of x that range from negative pi halves to positive 3 pi halves. You'll see why they chose this interval for x, because this interval is going to enable us to graph one cycle or one period of this particular sine function here. So what they do is they lay these values out on the x-axis, negative pi halves, the 3 pi halves, and they always try to find the 5 nice values that I alluded to yesterday. So negative pi halves is the first value on the x-axis, and 3 pi halves is the last value. The midpoint between negative pi halves and 3 pi halves would be what? What's 3 pi halves plus a negative 1 pi half? That would be 2 pi halves, which is pi, and pi divided by 2 is pi halves. So pi halves is the tick mark value that's dead center or in the middle between negative pi halves and 3 pi halves. Do we all understand how we got pi halves as the middle value? Anybody confused on that? How they got pi halves as the middle between negative pi halves and 3 pi halves? Anybody confused on that? Want to see how they got that, or are we convinced as to how they obtained that? I'm going to assume that unless anybody speaks up, that we do assume that we understand how we got that pi halves. Then you want to find the middle value between negative pi halves and positive pi halves, which when you add pi halves and negative pi halves together, you get 0, and 0 divided by 2 is 0. So 0 is in between these two values. Then they found the midpoint value between pi halves and 3 pi halves. 1 pi half plus 3 pi halves is 4 pi halves, but 4 pi divided by 2 is 2 pi, but 2 pi divided by 2 is pi. So pi is in between these two values here, pi halves and 3 pi halves. So do we understand how we got those 5 values there? Starting with negative, knowing that we're going to start with negative pi halves and then the 3 pi halves. Do we understand how we got the other 3 values in here? Okay, then what they did is they then plugged these values into in for x. Ladies and gentlemen, remember what I said yesterday. Although for our sine or cosine function, we might be putting in different values for x by virtue of the fact that the period and or now a phase shift may exist. These 5 values still correspond to the 5 values of the basic trig function, in this case, the basic sine function. So this value would correspond to 0. This value would correspond to pi halves going into the sine x function. This value would correspond to pi going into the sine function. This value would correspond to 3 pi halves going into the basic sine x function. This value would correspond to 2 pi going into the basic sine x function. So this is one trip around the unit circle for this particular function. So when you put negative pi halves in for x, you can see that the argument becomes 0, just like I said. And the sine of 0 is 0. So negative pi halves 0 would be a point that lies on the graph of this sine function. You put 0 in for x, the argument simplifies down to pi halves. And the sine of pi halves or 90 degrees is 1. So 0, 1 lies on this graph. Put pi halves in for x, pi halves plus pi halves is pi. Sine of pi or sine of 180 degrees is 0. So pi halves 0 lies on the graph. You put pi in for x, the argument simplifies down to 3 pi halves. The sine of 3 pi half radians or negative or 270 degrees is negative 1. Hence pi negative 1 is a point that lies on the graph of the sine function. Finally, you put 3 pi halves in for x into the sine function. The argument simplifies to 2 pi. The sine of 2 pi, which is coterminal to 0, or 0 degrees, or 360 degrees, is 0. Hence, this point lies on the graph. So do you see how this value, negative pi halves, corresponds to 0? 0 corresponds to pi halves corresponds to pi corresponds to 3 pi halves, and 3 pi halves corresponds to 2 pi. One trip around the unit circle, 0 pi halves, pi, 3 pi halves, 2 pi. All right, so we plot these points and connect them with a nice smooth curve. And you can see the graph of y equals sine x plus pi halves is in red here. And this is the blue graph, which is the graph of the basic sine function, y equals sine x. Ladies and gentlemen, notice the difference between the red graph and the blue graph. The only difference is not the amplitude, not the period. The periods for both these functions, sine x and sine x plus pi halves, are still 2 pi. The only difference is that the red graph has been shifted to the left pi half units. Notice this point has been shifted to the left pi half units. The maximum point on the blue graph has been shifted to the left pi half units. The minimum point on the blue graph has been shifted to the left pi half units. So by adding pi halves to x in the sine function, the graph of this new sine function experiences what is called a phase shift, or a horizontal phase shift. So we say that these two graphs here, the red and the blue graph, are out of phase by pi half radians. They're out of phase by 90 degrees or pi half radians. Does that make sense what happened here? So we've experienced a horizontal phase shift in y equals sine x by forming this new function by adding pi halves to our input value of x. Notice, ladies and gentlemen, if you were to continue this red graph all the way to 2 pi, it would max out here at 2 pi. And if you were to just to consider from 0 to 2 pi, the red graph, you would have the graph of the cosine function. Because remember I said yesterday, the cosine function, being the cofunction of the sine function, is 100 is pi half radians, or 90 degrees out of phase with the sine function. In other words, what I'm trying to say here, ladies and gentlemen, is what angle is complementary so you got the sine of x here, okay? What angle is complementary to x? That would be pi half radians minus x. So you can see the red graph here really would be the graph of the cosine function. And but don't get me wrong, it is the graph of sine x plus pi halves. So this red graph is out of phase by 90 degrees or pi half radians compared to the blue graph. Okay. So nonetheless, sine x plus pi halves has experienced a phase shift of negative pi half units to the left. So this whole blue graph has been shifted to the left pi half units. Do we understand what's happened there? Okay. All right, so we will now summarize as we build these functions up to more complicated functions. In general, the graphs of y equals a times sine of bx plus c, or y equals a times cosine of bx plus c, where b is assumed to be positive, have the following characteristics. The amplitude is always the absolute value of whatever number a is out here. We've seen that yesterday. The period of the sine or cosine function is always 2 pi divided by b, whatever b is. But we have some new number today. And that's this plus C here, which just becomes part of the argument of the sine or cosine function. This C influences or affects what is called a horizontal phase shift that exists with the graph. And the phase shift, which is really understood to be a horizontal phase shift, is negative C divided by B. So if you take the opposite of whatever number C is and divide it by B, ladies and gentlemen, you get the horizontal phase shift that the graph of these new sine or cosine functions experience relative to the graph of the basic sine x or cosine x function. So this is pretty important to remember here. What I cover here in these PowerPoint slides are also found in your section in your textbook. So this is also laid out again in section 4.3. And again, I would strongly recommend that you look over the sections by looking over the examples and maybe some of the definitions and important properties that are being laid out. Okay. So ladies and gentlemen, how would we graph y equals 2 times sine of 3x plus pi manually? Right now, here are some steps that we're going to go through to graph one period or one cycle of this sine function. First of all, we would like to know the amplitude of this sine function. And the amplitude is the absolute value of this 2 here, which gives you an amplitude of 2. The period of this sine function is 2 pi divided by b, b being 3. So the period is 2 pi thirds. The phase shift, there is a horizontal phase shift, and the horizontal phase shift is going to be negative c divided by b. So negative pi divided by 3. So the graph of this sine function will be shifted to the left pi third units compared to the graph of the basic sine x function. But how do we lay out or determine those 5 nice values that would be the input values into graphing one period of this sine function? Well, we're going to show you how to do this now. Ladies and gentlemen, the first thing you do is on your x-axis, your first tick mark value is always going to be your horizontal phase shift value. Let's go back here. Notice my horizontal phase shift is negative pi thirds. That becomes the first tick mark value that we establish on the x-axis, the horizontal phase shift, negative pi thirds. The last tick mark value we have on the x-axis would be the period. Okay, the period added to the phase shift. So 2 pi thirds added to negative 1 pi thirds. What's 2 pi thirds plus negative 1 pi third?
Pi thirds.
Pi thirds. So the last tick mark value of the 5 we establish would be pi thirds. So again, just to re-emphasize, the first tick mark value is always the horizontal phase shift value. You see, yesterday, ladies and gentlemen, that's why we always started with 0 as the first tick mark value. The reason why we always started with 0 is because we never had any number plus c out here yesterday. It was always, our c was always 0 out here. We just graphed like 2 sine 3x. We never had like 3x plus some value. That's why we never had any phase shifts yesterday. That's why our first tick mark value yesterday was always 0. Well, that changes today because now we have a horizontal phase shift with this function. It's negative pi thirds. So negative pi thirds again is the first tick mark value. The last tick mark value is the phase shift plus the period of the function. So negative pi 1 pi thirds plus 2 pi thirds is 1 pi third. To get the other 3 tick mark values, we just have the intervals. So we take the halfway or the midpoint of negative pi thirds and pi thirds. If you add negative pi thirds to pi thirds, you get 0. And 0 divided by 2 is 0. So 0, ladies and gentlemen, is the dead center tick mark value between negative pi halves and pi thirds. I'm sorry, negative pi thirds and pi thirds. To get the midpoint value of negative pi thirds and 0, you add negative 1 pi thirds to 0. And 0 plus negative 1 pi thirds is negative pi thirds. And then you divide by 2. So let me show you what they did there. They took negative pi thirds plus 0, and then they divide that by 2. That's how you find the midpoint between these two values here. This is going to be negative pi thirds divided by 2, which is negative pi thirds divided by 2 over 1, which is negative pi thirds times 1/2, which is negative pi sixth. So negative pi 6 is dead center between negative pi thirds and 0. Negative pi 6 is the midpoint between 0 and negative pi thirds. So therefore, negative pi 6 is in between 0 and negative pi thirds. In a similar fashion, to find the midpoint value between 0 and pi thirds, you could do it either based off of symmetry. If negative pi 6 is between 0 and negative pi thirds, you know positive pi 6 must be between 0 and positive pi thirds. Or if you don't believe me, 0 plus pi thirds is pi thirds. Pi thirds divided by 2 is pi 6. So ladies and gentlemen, these would be the 5 nice values that will go into our function that will correspond to one trip around a unit circle using the quadrantal angle values for the basic trig function. Negative pi thirds will correspond to 0. Negative pi 6 will correspond to pi halves. 0 will correspond to pi. Pi 6 will correspond to 3 pi halves. And pi thirds will correspond to 2 pi, one trip around the unit circle. So this then would be the graph of y equals 2 times the sine of 3x plus pi. Again, if I put negative pi thirds in for x, 3 times negative pi thirds is negative pi, and negative pi plus pi is 0. And the sine of 0 is 0. That's why this point starts here at negative pi thirds 0. When you put negative pi sixth in for x, what's 3 times a negative pi over 6? That'll be negative 3 pi over 6, which is negative pi halves. Negative pi halves plus pi is pi halves. This value corresponds to pi halves on the unit circle. And the sine of pi halves, or the sine of 90 degrees, is 1, and 1 times 2 is 2. So negative pi 6, 2 would be that point on here on the graph here. When you put 0 into this function, 3 times 0 is 0. 0 plus pi is pi. So this value 0 corresponds to pi on the unit circle. And the sine of pi, or 180 degrees, is 0. 0 times 2 is 0. Hence 0, 0 is a point that lies on our graph. And when you put pi sixth in for x, this 3 multiplied by pi 6 is 3 pi over 6, which reduces down to pi halves. Pi halves plus pi is 3 pi halves. So pi 6 corresponds to 3 pi halves on the unit circle for the basic sine function. And the sine of 3 pi halves is negative 1. Negative 1 times 2 is negative 2. That's why we have the point down here, pi 6, negative 2. What value is pi thirds going to correspond to? Anybody? On the unit circle for the basic sine function. By the time we get to pi thirds, it's like we've gone to what value on the unit circle?
2 pi.
2 pi. 3 times pi thirds is 3 pi thirds, which is pi. Pi plus pi is 2 pi. The sine of 2 pi is 0. 0 times 2 is 0. That's why we end one cycle or period of this graph right here at the point pi thirds comma 0. You are looking at the graph of one cycle or one period of 2 times sine of 3x plus pi. And this graph, ladies and gentlemen, if you were to compare it with the graph of sine x, y equals sine x, this red graph will have been shifted to the left. The graph of this red graph is the graph of the basic sine x function shifted to the left by pi third radians. Notice the amplitude of this graph is 2, 2. If you take the maximum point, 2, subtract off the minimum point on the graph, which is -2 for y. So 2 subtract the -2 is 2 plus 2, which is 4. 4 divided by 2 is 2. So the amplitude of this graph is 2 here. Remember how we found the amplitude? By using the graph, we take the maximum point, maximum y value, subtract off the minimum y value on the graph, take the absolute value of that difference and divide by 2. The maximum y value on this graph is 2. Subtract the minimum y value in this graph is -2. 2 subtract the -2 is 2 plus 2, which gives you 4. The absolute value of 4 divided by 2, ladies and gentlemen. Absolute value of 4 divided by 2 is 2. So your amplitude is 2. Okay. Okay. So in general, ladies and gentlemen, this is how you always lay out the 5 nice values that go into your trig function. The first value is always going to be the phase shift value, your -c over b value. The last value of the 5 tick mark values is always going to be the phase shift plus the period. To find this value c, that's the midpoint value in between A and E. So to find this value c, you take A and add it to E and divide by 2. Then to find this value b, which is the midpoint value between A and C, you add A and C together and divide by 2. To find the midpoint value between C and E, you add C and E together, divide by 2. You see how we always establish the 5 nice values for any sine or cosine function. All right. Okay. So how would we do this one here? Graph 1 complete cycle or 1 period of 5 times the sine of pi x plus pi fourths. What would we do then? Well, first of all, we can determine some attributes of the graph just by looking at the equation, the function. The amplitude will be 5, the absolute value of 5. The period is going to be 2 pi divided by b, which is pi. 2 pi divided by pi is 2. That'll be the period of this function. The phase shift, horizontal phase shift, will be -pi force divided by pi. -pi force divided by pi is the horizontal phase shift. -c divided by b. And that gives you a horizontal phase shift of -1/4. All right, so ladies and gentlemen, how do we establish the 5 nice tick mark values? Well, the first value we establish on the x-axis is the horizontal phase shift value, -1/4. The last of the 5 tick mark values is going to be the period, which is 2, plus the horizontal phase shift, -1/4. What's 2 plus -1/4? What's 2 plus -1/4? It gives you 8 force plus a -1/4, which gives you 7 force. Ladies and gentlemen, the last tick mark value is 7 force. Now to find the other 3 tick mark values, you find the midpoint between -1/4 and 7 force. What's -1/4 added to 7 force? Anybody? -1/4 plus 7 force.
6 force.
6 force, and 6 force. All right, 6 force divided by 2 is 3 force. Let's convince ourselves here. 6/4 divided by 2. Now, I know this seems elementary to go over these fractions, but ladies and gentlemen, fractions are usually our greatest weakness in mathematics, unfortunately. So 6/4 divided by 2 is 6/4 divided by 2/1, which is 6/4 times 1/2, which is 6/8, which reduces down to what? 3/4. Okay, you could have gotten there a little quicker, knowing that this 2 divides into the 6 rather 3 times. So 2 divides into itself once, divides into 6 3 times, and the 4 just drops down into the denominator. 3/4. All right. So the midpoint value between -1/4 and 7/4 is 3/4. To find the midpoint between -1/4 and 3/4, you add these together. -1/4 added to 3/4 is 2/4. And 2/4 divided by 2 is 1/4. 2/4 divided by 2 is 1/4. So 2/4 divided by 2, shortcut. 2 divides into itself once, divides into this 2 up here once. The 4 just drops down into the denominator. You got 1/4. 1/4. The midpoint between 3/4 and 7/4, 3/4 plus 7/4 is 10/4. And 10/4 really reduces down to 5/2, and 5/2 divided by 2 is 5/4. Now we have our 5 nice input values into our function. Look at this. -1/4, when you put that in for x, corresponds to 0 on the unit circle, and the sign of 0 is 0, and 0 times 5 is 0. That's why we got the point here at -1/4, 0. By the time you get to 1/4, ladies and gentlemen, if you put 1/4 in for x here, this argument will simplify down to pi-half radians. The sign of pi-halves is 1, and 1 times 5 is 5. We're up here at the maximum point. You put 3/4 into this function for x, that corresponds to pi radians on a unit circle. The sign of pi radians is 0. 0 times 5 is 0. That's why we're at this point. You put 5/4 into x, this argument, I guarantee you, will simplify down to 3 pi-half radians. The sign of 3 pi-half radians, or 270 degrees, is -1. -1 times 5 is -5. That's why we're down here at this point. You put 7/4 in for x, you simplify this, I guarantee you this will simplify to 2 pi. The sign of 2 pi is 0. 0 times 5 is 0. That constitutes 1 trip around the unit circle for this sine function here. This is analogous to 0. This input value is analogous to pi-halves. This input value is analogous to pi. This input value is analogous to 3 pi-halves. This input value is analogous to 2 pi. 1 trip around the unit circle. And we have the graph of 1 cycle of the sine function. And notice the amplitude is indeed 5. Because the absolute value of 5 subtract the -5 is 10. And 10 divided by 2 is 5. The amplitude is 5. All right. There are times when a sine or cosine function could experience a vertical translation. And ladies and gentlemen, how does that occur? Well, that occurs if you add or subtract some number from the entire sine or cosine function. If you look at this one here, y equals 3 plus 5 sine pi x plus pi-4. This positive 3 out here, ladies and gentlemen, is going to be a vertical translation. Because think about it, you're going to be adding 3 to the output values of whatever you get with this sine function. And when you add 3 to the y output values of this sine function, that's going to increase the overall y value by 3 units. That's going to ultimately shift the graph upwards by 3 units. So let's revert back to this example 7. Notice we graphed 1 cycle of 5 sine pi x plus pi-4. If I add 3 to this function, ladies and gentlemen, if I add 3 to this function, this red graph is going to be shifted upwards 3 units. The period will be preserved. Nothing changes with the period. Nothing changes with the amplitude. It's just that the whole graph gets shifted upwards 3 units. And you can clearly see that if you add 3 to the previous function we just seen in the previous slide, you get the red graph. And the red graph differs from the graph of the blue graph. The blue graph being from this function right here, in the sense that it's been shifted upwards 3 units. A vertical translation has occurred. Notice both graphs are still in phase with one another, meaning their periods are identical, their amplitudes are identical. Okay, it's just that the graph of this new sine function has been shifted upwards 3 units relative to the graph of this sine function. In a similar fashion, if you were to just graph y equal to 5 of sine pi x plus pi fourths, you would get this blue graph. The graph of one period of y equals 5 times sine of pi x plus pi fourths would be this blue graph. If you add -5 to that function, the graph of this new function, now this new sine function, would be this red graph, which has experienced a vertical displacement or translation of 5 units downward from the blue graph. Notice both graphs are still in phase with one another, meaning they still have the same period. The max and min still occur for the same input values. All right. So ladies and gentlemen, when you add or subtract a number from your sine or cosine function, that causes a vertical translation to occur with the graph. Any questions about this here? All right, let's wrap up this PowerPoint presentation by answering some questions here. And notice you got your choices up here. Fill in the blanks. Number 1, the phase shift of a graph can also be thought of as a blank translation. Anybody? What goes in for the blank? Haley, are you with us this morning?
Is it horizontal?
Horizontal, you are correct. The phase shift, when they say phase shift of a trigonometric graph, that is also implying it's a horizontal phase, horizontal translation or phase shift. All right, number 2, the graph of y equals sine of x plus pi thirds will have a blank shift equal to -pi thirds. We'll have a blank shift. What goes in for the blank? We already used the word horizontal, so scratch that word off.
It's gonna be phase shift.
Phase, exactly, phase. Because look at, if you take, this is your C value, all right? The opposite of C is -pi thirds divided by B. B is 1. 1's being multiplied by X. So your horizontal phase shift or your phase shift or your horizontal translation would be -pi thirds divided by 1, -pi thirds. So that's just the phase shift. Number 3, the graph of y equals 2 plus sine x will have a blank translation equal to 2. What goes in the blank? What word? Anybody?
Vertical.
Vertical. Yeah, by adding 2 to the sine function, that causes the graph of the sine x function to be shifted vertically upwards 2 units. Finally, well, how can we miss on this one? Number 4, the graph of y equals 3 sine 2x plus pi thirds will go through one complete cycle, one complete cycle in pi units. How did they get the period as pi? They took b, 2 pi and divided it by b. 2 pi divided by 2 is pi. Pi is the period of this function. The blank of the graph will be 3. What's 3 for the graph here? 3 is the what?
Amplitude.
Amplitude. The absolute value of the 3 is the amplitude. And the blank shift is -pi 6. -pi thirds divided by 2 is -pi 6. So the blank shift what would go in the blank? -pi 6 is what for the sine function? It's
The phase shift.
that'd just be phase shift. Actually, One of these used more than once in answering all these questions here. Okay, there you go. Okay. Let's see, ladies and gentlemen, if we can graph a couple of these. All right. We're gonna walk through a couple of these manually here. So these would be like typical problems that you could face in the future here. So let's just try to graph one period of y equal to 3 cosine 2x minus pi thirds. Okay, so how are we going to graph one period or one cycle of this cosine function? Well, to graph it manually, we need to lay out our 5 nice tick mark values. First of all, what would be the amplitude of this cosine function?
3.
The absolute value of 3 would be 3. Period is going to be 2 pi divided by 2 here, which gives us a period of pi. And phase shift. Is there any phase shift here? That's going to be the opposite of negative pi thirds. Careful with all your signs here. It's the opposite of negative pi thirds. The opposite of negative pi thirds divided by 2. So it's negative c divided by b. So when you simplify this, you'll have pi thirds divided by 2. 3 drops down and gets multiplied by the 2. So your phase shift is pi sixth. So your horizontal phase shift is pi sixth. All right, so ladies and gentlemen, help me out here. I'm going to start to lay out these values on the x-axis. What would be the first tick mark value that I lay out on the x-axis? What's my first tick mark value? Anybody?
Pi 6.
Phase shift. Phase shift is always the first tick mark value, so that'll be pi 6. So we'll put it maybe right here. My last tick mark value is what? Of the 5, what's my last one? Last tick mark value is going to be your phase shift, which is pi 6, plus your period, which is pi. Pi is another name for 6 pi 6. So what's 1 pi 6 plus 6 pi 6? 7 pi 6. So the last tick mark value is 7 pi 6. Now to find the other 3, we have the intervals. So what's the midpoint between pi 6 and 7 pi 6? 1 pi 6 plus 7 pi 6 is 8 pi 6. 1 pi 6 plus 7 pi 6 is 8 pi 6. You can reduce 8 pi 6 down to 4 pi thirds if you want. But then, ladies and gentlemen, we got to divide this by what? Got to divide by 2. 3 comes down and gets multiplied by the 2, so 4 pi 6, which reduces down to 2 pi thirds, would be the dead center point between pi 6 and 7 pi 6. So 4 pi 6 or 2 pi thirds. Now we got to find the midpoint between these two values. Pi 6 plus 2 pi 6. 2 pi thirds rather. Pi 6 plus 2 pi thirds. Or you could think of 2 pi thirds as being its unreduced form of 4 pi 6. So pi 6 plus 4 pi 6 is 5 pi 6. Pi 6 plus 4 pi 6 is 5 pi 6. And then we divide that by 2. 6 comes gets multiplied by the 2 down here. And so we have 5 pi 12s. 5 pi 12s. Now the midpoint between 2 pi thirds and 7 pi 6. Well, 2 pi thirds in unreduced form was 4 pi 6. 4 pi 6 plus 7 pi 6 is 11 pi 6. 11 pi 6 divided by 2 is 11 pi 12s. 11 pi 12s. Okay, ladies and gentlemen, we can now graph this thing. We know the amplitude is 3, so we're going to have a positive 3 and we're going to have a what? A negative 3 here on our y-axis. Ladies and gentlemen, pi 6 corresponds to, if I put pi 6 in for x here, I'm only going to do one of these here. If I put pi 6 in for x, watch what happens. I'll have 2 times pi 6 minus pi thirds. The argument simplifies down to what? What's 2 times pi 6? That'll be pi thirds. What's pi thirds minus pi thirds? 0. And the cosine of 0 is 1, and 1 times 3 is 3. So at pi 6, we're up here at 3. Ladies and gentlemen, think about it. We walk around the unit circle one whole time as we go from pi 6 to 7 pi 6 for this cosine function. We walk around the unit circle, the quadrantal angles, one time. Pi 6 corresponds to 0. 5 pi 12s will correspond to what value? Unit circle. We go from 0 to what? What's the next value in the unit circles? We walk around one time. 0 to for the basic cosine x function. If I was to graph the basic cosine x function, the 5 quadrantal angle values, I'm going to walk in around the unit circle once, would be 0, pi halves, pi, 3 pi halves, 2 pi, right? So 5 pi 12s corresponds to what? Pi 6 was 0, so 5 pi 12s will be what?
That would be pi halves.
Pi halves. And the cosine of pi halves of 90 degrees is 0. 0 times 3 is 0. The point's down here now. 2 pi thirds, ladies and gentlemen, 2 pi thirds corresponds to pi. And the cosine of pi is -1. And -1 times 3 is -3. So we're down here. 11 pi 12s, I guarantee you, if you put 11 pi 12s in there, multiply it by 2 and subtract all pi thirds, 11 pi 12s will simplify to 3 pi halves. And the cosine of 270 degrees or 3 pi over half radians is 0. 0 times 3 is 0. We're back up here on the x-axis. 7 pi 6, I guarantee you, if you put 7 pi 6 in for x, multiply it by 2 and subtract pi thirds, you'll have 2 pi. And the cosine of 2 pi is the cosine of 0 degrees or 360 degrees, which is 1. 1 times 3 is 3. We're back up here. Ladies and gentlemen, you are looking at the graph of one cycle or one period of this complicated cosine function. Everybody see that there? That's the graph of one cycle or one period of 3 cosine 2x minus pi thirds. So look at, my point is this, ladies and gentlemen, when you lay these 5 nice tick mark values out, you don't have to plug them in for x and go through the arduous evaluation, because we know the first tick mark value always corresponds to 0 for the basic sine or cosine function. The second tick mark value always corresponds to pi halves. Third tick mark value always corresponds to pi. The fourth tick mark value always corresponds to 3 pi halves. The last tick mark value always corresponds to 2 pi. One trip around the unit circle. One trip around the unit circle. Do we understand that there? So it's a waste of time to plug these in and, go through all the gory arithmetic details. First value corresponds to 0, second pi halves, third to pi, fourth to 3 pi halves, last to 2 pi. Always works that way for a sine and cosine function. That's why we call these the 5 nice input values into any sine or cosine function. Okay. Now, do we understand how we graph this function manually? The procedure we went through in graphing that manually. Ladies and gentlemen, I'll call this function y sub 1. So this is y sub 1. What if I develop a new function called y sub 2? And my new function is going to be this. It's going to be -1 plus 3 cosine 2x minus pi thirds. How will the graph of y sub 2 differ from the graph of y sub 1? Anybody? How are they going to differ? How will the graph of y sub 2 be different than y sub 1? Trent, you with us this morning?
Yeah, I'm with you.
What do you think? I just graphed 3 cosine 2x minus pi thirds. There's the graph of one cycle or period of it. How would the graph of this new function, by adding -1 to this function, how would its graph differ from this one? What do you think?
Would the points drop down one?
That's right. By adding -1 to my original cosine function, that forces the graph of this new cosine function to experience a vertical translation of 1 unit downward. Nothing changes with the period of this guy. Nothing changes with its amplitude. Still the same. So the graph of y sub 2 will still be in phase with the graph of y sub 1. It's just that it will be shifted down 1 unit. So this point will go down 1 unit. This point will be shifted down 1 unit. This point will be shifted down 1 unit. This point will be shifted down 1 unit. And this point will be shifted down 1 unit. And therefore, ladies and gentlemen, the graph of y sub 2 will be this graph right here. There's the graph of y sub 2. Notice it's the graph of y sub 1 shifted downward 1 unit. A vertical translation has occurred. Still in phase, however, with the other graph. Okay. Still in phase. Now, of course, if you were to continue these graphs, keep in mind all these graphs that I graph one period or cycle of, they continue. So you could conceivably graph more than one cycle or one period. So this thing would continue, to do this number forever to the right and left. And likewise, this will continue to do its thing to the left forever as we keep cycling around a unit circle. Okay. But we're just graphing one period or one cycle. All right. And of course, we can have some, we can always have some fun on the calculator too. If my calculator is running this morning. Mode, make sure you're in radian mode, ladies and gentlemen. Wait a minute, can we all see this calculator? Can
See
anybody?
it.
Okay, we're good. Radian mode. Let's go to y equals our equation editor. Let's clear out all the garbage that we may have in there. Let's go to y sub 1. All right. Let's type in the basic cosine function, cosine x to start. Let's have notice the period of this function is 2 pi, the amplitude is 1, there is no phase shift, there's no vertical translation. None of those things. This is your basic as it gets for your cosine function. Go to window, have x go from 0. Actually, I'll tell you what, I'm going to graph more than one cycle. I'm going to graph 2 cycles. So I'm going to go from -2 pi to 2 pi on the x-axis. And I want my tick marks spaced by, they will be spaced pi half units apart. Pi divided by 2. All right, my amplitude, I'm gonna just leave on y-axis from -3 to 3. So here's the graph of 2 cycles or 2 periods of cosine x. That's the graph of 2 periods from -2 pi all the way up to +2 pi. All right, let's have some fun now. Suppose I leave that function intact. I go down and I type in another function here. Okay, ladies and gentlemen, if I wanted my graph to be shifted pi half units to the right, what function do I type in? Help me out, anybody. I want the graph of cosine x just to experience a horizontal phase shift of pi half units to the right. What would be my new function? Anybody?
Would it be y sub 2 is equal to cosine of x plus pi over 2?
Exactly. Wait. Would it be plus pi over 2?
If you want to shift to the right, no.
Yeah, I want to go to the right.
Minus.
Yes, minus. They're very important here. Minus. Okay. Pi. Wait a minute. Hold on a second here. Pi divided by 2. Close parentheses, close parentheses. Okay. So yeah, see, ladies and gentlemen, now look at this new function here, x cosine x minus pi halves will experience a horizontal phase shift of, remember, the horizontal phase shift is always the opposite of what C is divided by B. The opposite of a negative pi halves divided by 1 would be a positive pi halves divided by 1, or pi halves. So this graph should be shifted pi half units to the right compared to the graph of the basic cosine function. Let's find out. Does it appear that the graph of y sub 2 is shifted pi half units to the right? It certainly does appear to be the case here. Okay. Tell you what I can do here. If I move my cursor way over to the left on y sub 1, to the left of y sub 1, and if I change if I hit enter, ladies and gentlemen, you can change what kind of mark you have here that will delineate the graph. Wait a minute, I don't want that. I just want a dash line. Everybody see that there? I changed from a solid to a dash line for y sub 1. So let's hit the graph now. Well, that's supposed to be a dashed curve here for the graph of y equals cosine x. It's not as dashed as I would like it to be. And the other one is supposed to be a solid curve. So I don't know. It'd be great if the screen was in color. That'd be even better. But we don't have that luxury. You can clearly see, however, ladies and gentlemen, that the graph of y sub 2 is shifted by pi half units to the right of the graph of y sub 1. Okay. All right. So let's clear this out. Okay, what function would I type in if I wanted the graph of cosine x to be reflected about the x-axis? Anybody? What would be my new function if I wanted cosine x to be reflected about the x-axis? To be reflected or flipped about the x-axis, what function would I type in?
Negative cosine x.
Negative cosine x. This we seen yesterday. Negative cosine x. Let's now graph these. Here's the graph of basic cosine x. Here comes the graph of negative cosine x. Notice it's the flipped version. It's been flipped about the x-axis. So, ladies and gentlemen, are these waves in phase or 180 degrees out of phase? What would be the case here? In phase or out of phase?
180 degrees out of phase.
Totally out of phase. Check this out. On a lake or like an ocean or a river or whatever, a pond, if you had two waves come together and coincide just like this, you would get what's called destructive interference. The crest of the first wave would cancel with the crest, with the lull or the bottom of the second wave. This crest would be nullified by the minimum or the trough of this wave here. So if you were to add all these y, think about it, ladies and gentlemen, if you were to add the y coordinates of both these functions together, what would be the graph we would experience if you were to add these two functions together? If I was to add these functions together, what kind of graph would we be looking at? Anybody? Think about it. If you add this y value up here to this y value down here, what's the sum of these two y values here?
Just gonna be zeros, which would
Zero.
just be a straight line.
Which, that's right. If you add these two functions together because they're 180 degrees out of phase, you get total cancellation as far as the y values are concerned. In other words, if two waves came together on a lake in, that mimic this phase regime, the water would be perfectly calm because this crest cancels with this trough. This crest cancels with this trough. This y value right here on this graph would cancel with this y value down here. I'll prove it to you. Let's add these functions together. Ladies and gentlemen, go down to y sub 3. Watch this. Hit vars. Go over to y vars. Function. We want y sub 1 added to y sub 2. Go to vars, y vars, function, y sub 2. So later on, when I add these two previous functions together, the graph of y sub 3 should be the horizontal line y equals 0. And if you don't believe me, I'm going to turn graphs y sub 1 and y sub 2 off so we don't see them. Just turn them off. We're not deleting them. We're just turning them off by moving the cursor on the equal sign, hitting the enter button. They've been turned off. Now watch, when I graph y sub 3, what should we see? We should see nothing. Because, ladies and gentlemen, the graph of y sub 3 is the x-axis. It's the graph of y equals 0. That's why if you had two water waves that came together, or sound waves, or light waves, ladies and gentlemen, or light waves. If you had two waves come together, whatever the waves are, water waves, sound waves, light waves, doesn't matter. You would get perfect cancellation. So if these were two light waves that came together, they would cancel each other out. I know we've all seen this before. On a sunny day, if you look at the bottom of a pool, ladies and gentlemen, where there's ripples on the surface of the pool water, do you agree there's times on the bottom when you see very bright lines and then you see black lines? Have we all experienced that before on the bottom of a pool? When you got ripples, you got some waves on the surface of the pool in bright sunlight. Do you agree sometimes you see very bright lines and you see black lines? We've all seen that before?
Yes, sir.
Here's what's happening. When you see the black lines for one instant in time, that means two light waves come together that are 180 degrees out of phase, and so they cancel each other. And that's why you have no light. That's why they're black in color. Ladies and gentlemen, if you have two waves that come together that are in phase with one another, okay, now what does that mean? Well, let me show you an example of two waves that are in phase with one another. Well, let me clear the garbage out. Okay. So what if I have cosine x versus 2 cosine x? These would be two waves that are in phase with one another. Everybody see that there? So ladies and gentlemen, if two light waves come together like this and are perfectly in phase with one another, the y coordinate value of this small amplitude wave would add to the y coordinate of the large amplitude wave, and the sum of the y coordinates would create another wave that would be even higher than these waves. Some of you don't even know what I'm talking about. Let me go down to y sub 3. Let me add these waves together for you and I'll prove it to you. I'm going to add y sub 1 and y sub 2 together. Okay, y sub 1 plus y sub 2. Everybody see that there now? Now here's what we're going to do. We're going to graph y sub 1, y sub 2, and y sub 3. Here comes the graph of the sum of y sub 1 and y sub 2. Ladies and gentlemen, what do you notice about the amplitude of the last graph, y sub 1 plus y sub 2? In other words, this point up here this y coordinate of this high point on the last graph up here is the sum of the y coordinate of the first graph added to the second y coordinates graph. You agree? We get what's called constructive interference here, where these waves reinforce each other. If you were to look at the bottom of a pool and you see a very bright line in one instant time, that means that two crests of a light wave have come together and reinforced each other. That's why it's very bright in one instant in time for that wave, because they are in phase and they reinforced each other. That's true not only for water waves or sound waves, it's also true for light waves, okay? So when waves are in phase, they reinforce each other. When waves are out of phase, they destroy each other, okay? All right, so I just wanted to drive home that very important point there. When waves are in phase with each other, in other words, the frequency of vibration of the wind against the bridge versus the frequency of vibration of the bridge, that's a bad thing. That's called resonance, where the waves can actually complement one another and reinforce each other, which can cause the bridge to vibrate uncontrollably and actually break up. That happened with the Tacoma Bridge. I forget, in Tacoma, Washington. I forget what year that was. Just type that in a YouTube video, the Tacoma Bridge breakup. You'll see what resonance can do, ladies and gentlemen, if it gets out of control. And that's why you got to control the concept of resonance when you're designing bridges or buildings, okay? Because if your waves come together in phase, an uncontrollable vibration can occur, which can destroy things. All right. Okay. All right, classwork for today. And you would definitely revisit resonance if you get into mechanical engineering or you get into civil engineering or structural engineering. So ladies and gentlemen, classwork. This is July 27th. I want you to, for problem number 1, I want you to graph one period. Of y equal to cosine x minus pi fifths. Please lay out your 5 nice tick mark values on your x-axis and then show me the graph of one cycle. Number 2, graph one period. Okay. So one period of y equal to 1 plus the sine of 2x minus pi. Go ahead and do those and we'll come back and we'll take a look at those. Classwork for July 27th today.